This brief will cover controls. Now, I don't want to insult your intelligence here. I realise that you've been flying for a while and you understand the effects of controls. The purpose of this brief is simply to revise a couple of the key concepts, which will help us to understand in more detail the impact that our control inputs will have on upset recovery. In this brief, we'll cover the effect of camber, the primary flying controls, trims, spoilers and speed brakes, and slats and flaps as high lift devices. Starting first with camber then. You'll recall from our brief about the principles of flight that when we revised terminology we looked at the camber line as being the imaginary line which is joining all the points which are equidistant between the top surface and the bottom surface of the wing, all the way between the leading edge of the wing and the trailing edge of the wing. The camber therefore describes the curvature of the wing. Referring back to our trusty coefficient of lift versus angle of attack graph, you'll remember that the lift generated by the wing is described by this blue line. If you look at the coefficient of lift axis, you'll see that the blue line actually crosses the axis not at the graph's origin, but slightly up. This means that at a zero angle of attack, we actually are still producing some lift in this particular wing. The reason for this is the camber. The fact that the wing is slightly curved means that it's generating some lift, even at zero angle of attack. If, however, we had a symmetrical airfoil, which is where the camber line is exactly in the same place as the chord line, because both halves of the airfoil, the top surface and the bottom surface, are exactly the same profile, then the lift line would cross the origin of the graph. That is to say that at zero angle of attack, there would be zero lift. This is useful for aerobatic aeroplanes, but not so useful for us in a transport category, where we're really looking to try and extract the maximum efficiency from the aerofoil. So you'll see the diagram at the bottom right here, the modern aft cambered aerofoil, is a typical cross-section that we may find in a modern business jet. This has been specially shaped to give the maximum lift with the minimum drag at our typical cruising airspeeds. Primary flying controls effectively use the ability to vary the camber of a wing in order to give us an effect on the aircraft by varying the lift on different surfaces. In this case, you can see that whichever control surface this is, and let's say maybe it's an aileron, because the aileron is deflected down, we've now increased the amount of camber on the wing. Looking at our coefficient of lift versus angle of attack graph again, we can see that for a non-deflected control, the graph is our familiar curve. As we deflect the control surface, we can see that the line now moves up and left as a result of the increasing camber. This means that the maximum lift that we can produce with this wing, with the increasing camber, has increased, but the stall, the critical angle of attack, will occur at a lower angle of attack. This is why it's so important not to make large aileron inputs at high angles of attack, because it is so easy to get the wing with a downgoing aileron to pass its critical angle of attack. Note also that the aileron of the downgoing wing will lose its effectiveness beyond the stall. This is because the aileron on that side will be deflected up, and if the airflow is no longer attached to the top surface, the aileron has lost its ability to influence the path of the airflow. Moving on to trims. An aircraft, we say, is in trim when we see that the sum of all forces acting on the aircraft is zero, and if the pilot releases the controls, the aircraft will continue on the desired flight path. For us in modern jet transport aircraft, we need to give the most consideration to the way that we trim the aircraft in longitudinal control. So that's all I will look at on this slide. There are three main methods in which modern jet transport aircraft trim in the longitudinal axis. The first of these is an elevator trim tab. The elevator trim tab, you will have seen, is effectively a smaller control surface which is deflected at the trailing edge of the main control surface. So in this case, let's consider this wing diagram to be the tailplane and the main control surface to be the elevator. The elevator trim tab will be the small surface which is projecting in the opposite direction to the deflection of the main elevator. The problem with this system is that whilst we can relieve the longitudinal forces on the aircraft within a set speed range, we still have a maximum deflection of the elevator, and when we trim the aircraft, we are trimming the elevator to sit at its displaced setting with no control force. This means that there is a smaller additional deflection available in one direction and a larger additional deflection available in the other direction, which is a significant factor when we think about how much control authority we're going to have to recover. The second main method of trimming is an all-flying tail. The all-flying tail is a very powerful control surface, and the trim in this case is set by moving the entire control surface to a new neutral position. The third main method is a trimmable stabilizer, and this has become the most frequently used in high-performance modern jet transport aircraft. In this case, the elevator at the back of the tailplane is the main surface which still gives us our control input, but as we hold a control force, the whole of the tailplane will retrim to a new position, allowing the elevator to return to a neutral position. This enables trimming over a wide speed range, but also allows us to have a tactile judgment of the remaining deflection available. If the stick is in the middle with no trim force, then we know that the elevator is in a neutral position relative to the rest of the tailplane, and therefore we have a known quantity of deflection available to us, nose up and nose down. Moving on now to spoilers and speed brakes. The purpose of this is to increase drag and spoil the wing lift by bringing a separation point of the airflow forward from the trailing edge of the wing. They are most effective at high speed or when the wing is producing the most lift, such as when the flaps are down. And they are ineffective when the airflow is already disrupted, such as when the wing is stalled. Finally, high lift devices, slats and flaps. Compared to our clean wing, our now familiar diagram, when we deploy flaps, wing, just as we saw when one of the primary control surfaces is moved, the lift versus angle of attack diagram will move up and left. This means that the critical angle of attack is reduced, but the maximum amount of lift available is increased. However, when we deploy slats, we'll find that the maximum amount of lift will increase, but so will the maximum angle of attack that we can achieve. And this is because the slats will assist the airflow to remain attached to the top surface of the wing for longer. This has been a very brief canter through the different control surfaces available to us. Make sure that you are aware of the control systems fitted to your aircraft and how they work, as a knowledge of the limitations and the method of operation of your control surfaces will be vital in understanding the correct recovery action to take. In the next video, we're going to move on to looking at manoeuvring flight.